Alright, hello fellow sapiens. Sit back, relax, and prepare to wander into the moment the Ice Age finally ended, the day the world flooded, and the planet we know was born. This is the day the Ice Age ended. What happened? When the world flooded told softly, for the mind to stay awake just a little longer than the rest. Welcome to Sleepless Homo, a quiet corner of the internet where we study deep time the way our ancestors once watched fire, slowly, patiently, without noise. Here, science moves at the pace of thought. Here, history is a calm companion, not a lecture. And here, you're never just a listener. You're another sapiens trying to understand how we became us. Now imagine this. You wake up in a world made of ice, not the kind that melts in your hand or cracks beneath your boots, but a continent-sized presence stretching beyond the horizon, a white silence so heavy it shapes the sky. For thousands upon thousands of years, nothing has moved here except wind, cold, and the slow grinding of ice against stone. Yet something is changing. A softness creeps into the air. A layer of snow feels slightly wetter underfoot. And if you listen long enough, you begin to hear it. A distant drip, faint as a heartbeat. The planet is warming. Not in a mythic way, and not in a way a hunter or gatherer must describe with theories, but in a way the body quietly understands. The world is beginning to melt. To place yourself in those final millennia of the late Ice Age is to imagine a landscape caught between endurance and collapse. Around 18,000 years ago, the northern hemisphere was still imprisoned beneath vast sheets of ice. Some were over 2 miles thick and wide enough to swallow entire regions of what we now call North America and Northern Europe. These ice sheets were not still monuments. They moved slowly, reshaping mountains, crushing forests, and carving valleys with the patience of time itself. They also held within them an unimaginable amount of water, locked away as snow and compacted ice, preventing the oceans from reaching the shorelines we know today. The world was colder, drier, windier, and the distribution of life itself followed the commands of climate rather than the freedom of choice. What ended this frozen world was not a single event but a complex shift, a combination of solar patterns, atmospheric changes, and ocean circulation that tipped the balance. Even now, scientists do not fully agree on every mechanism, and perhaps that is fitting. A planet is not a machine with one switch. It is a system of systems. Some changes are gradual, others are abrupt. All we can say with evidence is that around 18,000 years ago, something changed in the climate machine, and the direction of the world story began to tilt. One of the clearest signals comes from the Greenland ice cores. When researchers drill deep into ancient ice, they are not just slicing into frozen water, but into time itself. Each thin layer of snowfall, compacted by centuries and millennia, holds traces of the air that once swept across the planet. These bubbles, tiny and fragile, reveal the chemistry of ancient atmospheres, levels of carbon dioxide, methane, dust, and volcanic ash. And it is in this frozen record that we see the opening notes of the warming. Temperatures begin to rise, not dramatically at first, but steadily enough that the frozen world feels the shift. With warming comes movement. Ice sheets that once advanced begin to retreat. Their margins crack. Meltwater pools on their surfaces, carves channels, and drains into rivers that did not exist in the colder world. When ice melts, it does not simply vanish. It reshapes the earth. Rivers grow wild with new flows. Lakes expand across the land. Patches of tundra soften and give way to shrubs, then grasses. Animals follow these changes. Mammoths, reindeer, bison, and predators move with the transforming habitats, even though they cannot know the scale of the force guiding them. The cause of this warming is not entirely settled, and a humble scientist must acknowledge the uncertainty. but several clues offer a story written in geochemistry and oceanography. As the planet tilted in its long orbital cycles, sunlight began to strike the northern latitudes more intensely. This increased radiation slowly shifted the balance between accumulation and melt across the massive ice sheets. At the same time, atmospheric carbon dioxide levels began to rise, trapping more heat. Some of this carbon may have returned to the air as expanding oceans released gases stored in cold waters, a feedback loop that added momentum to the warming. Ocean circulation also played a critical role. The Atlantic meridional overturning circulation, the vast conveyor belt that moves warm water northward and returns colder, denser water southward, began to steady after a period of disruption. As this system regained strength, it allowed warm currents to bring more heat toward the northern hemisphere. The combination of sunlight, greenhouse gases, and ocean currents created a new climate reality. The world was no longer in equilibrium with ice. If you had lived in those years, you would not have known any of this. You would have known only what your body told you. Snowmelt occurring earlier each spring, the bite of winter softening by a few days, rivers running just slightly fuller, the migration of animals shifting by weeks. Humans did not measure climate with instruments then, but with attention. They would have felt the world loosening. What happened next is something scientists today can trace in sediments, shorelines, and the chemistry of ancient water. The retreat of ice is not smooth. It is a process filled with pauses and accelerations. When ice sheets thin, they become unstable. Cracks widen. Entire sections can break off, forming icebergs that drift into the sea. Beneath the ice, meltwater flows through tunnels and layers, carving new channels, gathering in basins and lifting the ice itself from the land. The entire system becomes fragile, responsive to temperature shifts too subtle for early humans to sense, but powerful enough to change continents. During these millennia, meltwater pulses begin to appear. These are periods when sea levels rise faster than the long-term average, triggered by sudden accelerations in glacial melt. They are not yet the great floods that would come later, and we will not speak of those now, but they are early hints that the world is capable of abrupt shifts. Geological evidence shows that these pulses were embedded within cycles of unstable ice retreat. Shorelines shifted not by entire coastlines vanishing overnight, but by slow, persistent changes that accumulated year by year. To understand the scale, imagine this. If all the ice-covering parts of North America and Northern Europe were to melt today, the sea would rise by hundreds of feet. Now imagine that ancient humans, walking along their familiar coastlines, did not know they were living on borrowed land. The ice sheets were still enormous in these early centuries of warming, still vast enough to command the weather. But the end had begun. The long-frozen world was unravelling, and this unravelling affected every ecosystem. As the ice sheets weakened, cold winds blowing from their surfaces lost their strength. Storm patterns changed. Dust that once blew freely across glacial plains decreased as moisture returned to the air. In places once barren, new vegetation began to grow. These shifts happened in rhythms slower than a human lifetime, but fast enough that generations could sense the edges of change. A grandparent might notice that winters were no longer as severe as the stories told by elders before them. A hunter might travel farther to find the same herds. A gatherer might observe new plants emerging in patches where none had grown before. The melting also reshaped the land in ways invisible without a long view. As glaciers retreated, they left behind moraines, boulders carried from distant mountains, and vast plains of ground rock called till. Rivers, suddenly released from icy constraints, carved fresh paths through newly exposed earth. Lakes formed in depressions once covered by ice, some of them enormous. Entire landscapes were created not by life but by water, freeing itself from the weight of ice. In the distance, the cracking of ice could echo across valleys, a sound ancient people might have heard without understanding its significance. A glacier carving is a thunderous event, a mixture of breaking, collapsing, and the roar of water rushing into newly opened space. Imagine hearing that sound for the first time, not knowing that it means the world is changing, only knowing that something immense has shifted far beyond the reach of human hands. The melting also reveals one of the more fascinating clues of this era: pollen. Layers of sediment across lakes and bogs preserve the remains of ancient plants. These microscopic grains tell the story of the returning forests. Tundra landscapes gave way to shrubs. Shrubs gave way to birch and pine. As temperatures rose, tree lines moved northward. Each pollen grain is a quiet testimony of the warming that changed everything. But warmth can also destabilize. As the ice sheets melted, their weight lightened. The land beneath them began to rise. This process, called isostatic rebound, is still happening today in parts of Scandinavia and Canada. The Earth's crust, once pressed down by unimaginable tons of ice, slowly lifted itself toward equilibrium. Rivers changed course. Lakes drained or filled as the ground tilted in subtle but consequential ways. A landscape that had been fixed for tens of thousands of years began adjusting all at once. For ancient humans living at the edge of these shifting worlds, the experience must have been a mixture of familiarity and surprise. They did not witness an apocalypse. They witnessed an awakening. A planet emerging from an era of cold into an era of motion. If you were there, you would not have said the Ice Age ended. You would simply have noticed that the world you knew was loosening, as if the long winter of Earth were slowly exhaling. And yet, with every exhale came a new uncertainty. Ice is stable. Melt is not. The planet was entering a phase where change accelerated faster than memory. The warmth that freed the world from its frozen bonds was an invitation to new landscapes, new migrations, new possibilities. But it was also a prelude to something far more dramatic, something the people of that time could not have imagined. Something written not in human stories, but in the layers of ancient coral reefs and the long curves of sea level rise charts. By the time the last centuries of this warming approached, the world stood on the threshold of a transformation. The ice sheets, once the architects of continents, were weakening. The climate was shifting toward a new equilibrium, and the stage was quietly setting for an event that would change coastlines across the planet, reshape ecosystems, and leave impressions deep enough to echo through the stories that came after. We will reach that moment later, but for now, it is enough to stand in those final centuries of the late Ice Age, feeling the drip of meltwater in the air, hearing the distant crack of ice, and knowing only that the world is changing in ways too vast for anyone to grasp. The frozen world is breaking, and the warm world is on its way. If you feel like supporting this kind of slow storytelling, the kind made for late-night thinkers, for drivers on long roads, for people who learn better when the world goes quiet, a gentle like and subscribe helps other sleepless minds find this place too. And tell me, where are you listening from? Are you in bed drifting off, at work with headphones, cooking, driving, or just trying to calm a busy mind? I read every comment, and if you fall asleep, the timestamps are waiting for you when you return. All right, let's continue, and as always, stay curious, stay calm. A planet locked in cold for tens of thousands of years suddenly begins to warm in a way no one alive could have predicted. Not gradually, not gently, but with a speed that feels almost impossible for a world so massive and so old. If Earth had a pulse, this would be the moment it quickened. And if you were alive between 14,000 and 12,900 years ago, you would feel it long before you understood it. The cold that shaped everything you knew would begin to loosen, not over centuries but within the span of a human lifetime. Seasons would shift, ice would retreat, animals would wander along new routes, and the great frozen engine of the world would begin to stutter. To understand this extraordinary moment in deep time, we must begin with the evidence that outlived every hunter, every migration, every generation that felt the change without knowing why. This evidence lies hidden in deep ice. When scientists drilled into the Greenland ice sheet and extracted cylinders of ancient snow, they did not retrieve frozen water. They retrieved memory. Layer upon layer, winter after winter, each snowfall trapped tiny bubbles of air and dust, preserving the atmosphere of long-lost worlds, and these layers show something remarkable. Around 14,000 years ago, temperatures in the northern hemisphere began rising far more rapidly than their slow glacial rhythm should have allowed. In some places, average temperatures jumped enough to transform landscapes within a few centuries. For a planet used to moving in geological time, this was a sprint. The ice cores tell us this in two ways. First, through isotopes. Water molecules containing heavier oxygen, isotopes evaporate and condense differently depending on temperature. When these heavier isotopes appear more frequently in ancient snow layers, it means the air was warmer when that snow fell. And what we see in the Greenland cores is a sudden enrichment of these isotopes. Not a gentle slope, but a step, abrupt and unmistakable. Second, dust levels change. In colder, drier climates, winds blow more strongly over exposed plains and glacial deserts, filling the air with fine particles. As the world warmed, moisture returned to the atmosphere, and dust levels dropped sharply. The shift in dust marks the shift in sky. But the ice cores alone are not the full story. Sediments from lakes and peat bogs across Europe and North America echo the same message. Pollen from birch and pine begins to appear where only tundra and cold grasses existed before. In just a few human generations, forests expand into regions that had been barren for thousands of years. Plant species begin migrating northward, following the path of retreating cold. And with plants come animals. The great reindeer herds that once roamed dry, frozen plains begin shifting their seasonal routes. Predators follow. The entire ecological web adjusts to the warming that no one can see, only feel. What caused this sudden spike? Here the evidence becomes a little quieter, and our certainty thins like melting snow. Part of the warming was the natural rhythm of the planet. Earth tilts, rotates, wobbles, and moves around the sun in patterns known as 𝐓𝐈𝐌𝐄𝐒𝐏 cycles. These cycles change how much sunlight reaches different latitudes at different times of year. Around 14,000 years ago, northern regions began receiving stronger summer sunlight, enough to tilt the balance between the growth and decay of ice sheets, and once a massive sheet of ice begins to melt, the process can feed on itself. Darker land absorbs more heat than bright ice. Meltwater darkens the surface further. The more ice disappears, the more warming accelerates. Atmospheric gases also played their part. Carbon dioxide levels, measured from ancient air trapped in ice, rise noticeably during this period. Whether this was caused by warming oceans releasing stored gases, or by slow changes in vegetation and soil is still debated. What we do know is that as carbon dioxide rises, so does the ability of the atmosphere to trap heat. The warming was not only solar, it was atmospheric. And in a world covered by ice, even a small increase in trapped heat is enough to shift the long-term balance. Another player in this story is the ocean itself, the great conveyor belt of warm and cold currents that moves heat around the planet seems to have been shifting during these millennia. As the ice sheets melted, they released enormous amounts of fresh water into the North Atlantic. This change in salinity altered how water sank and rose across the ocean, influencing global heat distribution. When circulation patterns shift, climate shifts with them. This can cause warming in some regions and cooling in others. But the overall trend across the Northern Hemisphere in this period is unmistakable. The world was heating up. This warming did more than raise temperatures. It destabilized everything built from ice. Glacial surfaces melted from above and below. Meltwater carved networks of channels, pooling in vast lakes that had no parallel in the modern world. Sheets of ice kilometres thick began thinning, cracking and retreating. These were not passive blocks of frozen water. They were dynamic, shifting bodies responding to the smallest changes in temperature. When enough meltwater accumulated at their bases, it acted like a lubricant, helping the ice slide more easily over bedrock. The movement of ice quickened. Retreat became inevitable. Imagine walking across a landscape you believed was eternal, only to find its edges dissolving season by season. Ice cliffs that once seemed immortal would begin to crumble. Streams that once froze solid would continue flowing later into autumn. The sound of water barely heard for millennia would return. And even if you did not know the science, you would know something fundamental was changing. Winter was losing its command. One of the most compelling pieces of evidence for the speed of this warming comes from ancient coral reefs. Corals grow upward towards sunlight. When sea levels rise, they grow faster to keep pace. By examining the height and age of fossil reefs in tropical oceans, scientists can reconstruct how fast seas were rising thousands of years ago. These corals show that the oceans responded rapidly to melting ice in the north. And although we will not yet speak of the great rises that came later, we can say with certainty the system was already unstable. As temperatures rose, ecosystems across continents transformed. The cold steppe landscapes, once home to enormous herds of grazing animals, became wetter. Grasslands gave way to shrubs, then forests. Species adapted to open, frozen environments found themselves displaced. Some retreated northward, others disappeared. A new world was forming on the remnants of an older one. Every creature had to decide in its own evolutionary way whether it would follow the warmth or resist it. For humans, these centuries would have been filled with subtle but relentless adjustments. The timing of hunts, the types of animals encountered, the plants that could be gathered, the length of winters and the rhythm of seasons. People did not think about climate. They thought about survival. But their survival was tied to a climate they could neither predict nor control. One small detail from lake sediments helps illustrate this transformation. As the climate warmed, insect species adapted to cooler environments began to vanish in many regions. They were replaced by species that preferred warmth. Their tiny remains, preserved in the mud of ancient lake bottoms, act like messengers from a world learning to breathe again. When insects change, birds change. When birds change, predators change. When predators change, humans must adapt in turn. Climate does not shift in isolation. It reshapes the entire web of life. We can imagine those humans walking across the thawing terrain with a strange mixture of familiarity and uncertainty. The world they knew still existed, but it no longer behaved as it once had. Rivers swelled with meltwater. New plants appeared in places that had been bare. Fog formed over newly exposed soils as warmth returned. And above all, the air itself felt different, softer, heavier with moisture, carrying scents unfamiliar to generations that had grown up under colder skies. What science tells us today is that by 12,900 years ago, the world had warmed substantially compared to its state at the height of the Ice Age. Forests spread, ice sheets retreated far inland, and the great climatic engine of the Northern Hemisphere had shifted into a new phase. But warming does not guarantee stability. A planet can tip in many directions, and its systems can respond in ways that surprise even the most careful observers. The centuries that followed this warming carried one of the sharpest climate reversals in human history, though we will not enter that story now. It's enough to remain in these centuries of rising temperatures and imagine a world shedding its long winter coat, one meltwater stream at a time. The truth is that we still do not fully understand every cause of this rapid warming. No single mechanism explains it perfectly. It was likely the interaction of orbital cycles, atmospheric gases, ocean circulation, and feedback loops within ice sheets. The evidence is clear, but the interpretation carries humility. A scientist must acknowledge what nature does not easily reveal. Climate can be as mysterious as it is measurable. What we do know is that these centuries mark a turning point. The frozen Earth was loosening its grip, and the stage was being set quietly and steadily for changes that would reshape coastlines, ecosystems, and eventually the course of human history. In a world waking from its long icebound sleep, nothing was yet dramatic, but everything was beginning. The world has just begun to thaw. Forests are pushing north, glaciers are retreating, rivers swell with new meltwater. The air feels softer than it has in thousands of years. Then, almost without warning, the warmth collapses. The shift is so sudden, so sharp, that if you measured it not in millennia, but in human breaths, it would feel like the planet inhaled and forgot how to exhale. Between 12,900 and 11,700 years ago, Earth snapped back into conditions astonishingly close to the Ice Age it had only just escaped. This return to cold is known as the Younger Dryas, and in the language of deep time, it was a shock. In the language of science, it was one of the most abrupt climate reversals ever recorded, and in the language of humility we can say only this: we still do not fully understand why it happened. The first clues lie once again in the Greenland ice cores. These ice archives show a breathtaking temperature plunge. In a matter of decades, perhaps even less in some regions, the Northern Hemisphere cooled dramatically. The isotope record reveals this shift with unmistakable clarity. Oxygen ratios change direction, dust levels rise, and the chemistry of the trapped air signals a return to the harsh conditions of a glacial climate. It is as if the planet reversed course mid-stride, pivoting back toward winter at a pace far faster than its warming had unfolded. To see this turn written in patterns of frozen water is to appreciate the sensitivity of the Earth system. Climate, for all its vastness, can be startled. Sediments from around the world echo this cooling. Pollen trapped in lake beds shows forests retreating almost as quickly as they had advanced. Species of shrubs and trees adapted to warmer environments suddenly vanish from the record. Cold-loving grasses and tundra plants reappear, reclaiming ground they had been losing for centuries. The ecosystems of the north had no time for slow adjustment. The line between a warming world and a cooling one was crossed in the span of a few human generations, a blink compared to the long rhythms of glacial cycles. Insects change first, then plants, then the animals that rely on them. The chain reaction is visible in every core of mud pulled from ancient lakes. What could have caused such a dramatic reversal? This is where the story becomes both fascinating and humbling. Several hypotheses exist. supported by varying degrees of evidence. None explain everything perfectly. The most widely supported scientific explanation focuses on the oceans, specifically the Atlantic meridional overturning circulation, the great conveyor belt that redistributes heat around the planet. As the world warmed before the Younger Dryas, massive amounts of fresh water were released from melting ice sheets. Too much fresh water entering the North Atlantic can disrupt the sinking of cold, salty water that drives the circulation system. If the conveyor belt slows, less warm water flows northward. Temperatures fall, winters deepen, climate patterns destabilize. In this view, the Younger Dryas was triggered by a sudden pulse of fresh water that essentially turned down the planet's northern heat engine. But here the puzzle deepens. The exact source, timing and volume of this fresh water remain debated. Some researchers point to the draining of enormous glacial lakes in North America, lakes that held more water than all of today's Great Lakes combined. Others look to massive ice collapses or rerouted meltwater channels. But the geological evidence is not perfectly aligned. Some freshwater indicators appear too early, others too late. As with many things in deep time, the truth may lie in a combination of factors rather than one dramatic moment. Another possible contributor is the atmosphere itself. Changes in atmospheric circulation, shifts in the position of the jet stream, or alterations in the distribution of sea ice could all have amplified the cooling once it began. When sea ice expands, it reflects more sunlight back into space, reinforcing cold conditions. Models suggest that once cooling reached a certain threshold, feedback loops strengthen the trend. Climate behaves like a web, not a line. Pull one strand, and many others move. Volcanism has also been suggested, though with less support. A large volcanic eruption can cool the planet temporarily by sending particles into the stratosphere that block sunlight. But no known eruption from this period appears large or sustained enough to account for the long duration of the Younger Dryas. Still, the possibility of smaller eruptions contributing to the initial cooling cannot be dismissed entirely. Deep time rarely offers neat explanations. Some scientists have explored more unconventional causes such as cosmic impacts or atmospheric disruptions, though the evidence remains contested. It is scientifically healthy to consider multiple possibilities, but it is equally important to anchor conclusions in what can be measured, not in what is merely dramatic. The Younger Dryas does not need an extraordinary cause to be extraordinary. The climate system is capable of stunning reversals on its own, without any external explosion or cosmic intervention. This event is impressive enough simply because of what Earth itself can do. Regardless of the cause, the consequences were global. In Europe, tundra conditions returned to landscapes that had only just begun to green. Permafrost re-established itself in places that had thawed. Glaciers, once in retreat, began to stabilize and in some regions even advance. Lakes cooled, and cold-adapted fish species regained dominance. In Asia, the monsoon weakened. In Africa, rainfall patterns shifted, altering lake levels and changing the distribution of plants and animals. South America shows signs of altered climate as well, though the response there was more complex. The Younger Dryas was primarily a Northern Hemisphere event, driven by changes in northern oceans and ice, but its echoes were felt across the world. One of the more striking pieces of evidence comes from ancient stalagmites in caves. These limestone formations record rainfall and temperature conditions in their layered structure. When researchers analysed stalagmites from China and South America, they found abrupt changes in their growth during the Younger Dryas. The pattern suggests that global atmospheric circulation shifted dramatically, rerouting moisture across continents. Cave formations become reluctant storytellers of a climate turning inward toward cold. Another line of evidence lies in the grain size of sediments deposited by ancient winds. During colder periods, stronger winds carry larger particles. Across the North Atlantic region, wind-blown sediments during the Younger Dryas become coarser, reflecting a world turning drier and windier. Glacial dust once again swept across exposed landscapes, settling into lakes and oceans as a fine record of returning cold. What makes the Younger Dryas particularly fascinating is not just the severity of the cooling, but its speed. The transition into cold appears to have happened in less than a century. Some ice core data suggest it may have been even faster, perhaps within a few decades. This does not mean the entire world froze overnight, but that the shift from warming to cooling was sharp enough for its signature to be etched clearly in geological archives. Earth, a planet often slow to respond, suddenly behaved like something with reflexes. The persistence of the Younger Dryas is equally striking. For more than 1,000 years the planet remained in this colder state. Forests stalled in their expansion. Ecosystems held their breath. Ice regained its grip, and the world hovered in a balance that no one living at the time could have interpreted. There were no instruments, no theories, no global perspective, only the evidence nature left behind for us to examine now. A record of cold returning for reasons still partly hidden. Eventually the Younger Dryas ended. The cold retreated almost as quickly as it had arrived. But we will save that moment for later. For now, it is enough to stay within this extraordinary 1,000-year pause. A world that had been warming was abruptly pulled back toward winter. A climate system that had been unlocking itself suddenly chose restraint. And the rhythms of Earth proved once again that they do not move for our understanding. They move because the planet is a restless and interconnected system, capable of shifts as subtle as a grain of pollen and as overwhelming as the return of ice. When we study this event today, we do so with humility. The Younger Dryas is a reminder that even with ice cores, sediments, corals, cave records, and climate models, our knowledge is always partial. We can trace the fingerprints of ancient climate. We can understand the sequences, but the pulse behind those sequences remains partly mysterious. Earth is old, and its memory is longer than our explanations. The Younger Dryas may seem like a distant event, a cold echo from a world before civilization, but it carries a simple truth. Climate is not a straight line. It is a pattern of balance and disruption, a dance between forces that sometimes change more quickly than the living things that depend on them. Imagine this. A world locked in sudden cold for more than 1,000 years begins to warm in a way that feels almost unreal. The change is not subtle. It does not creep. It arrives like a breath the planet had been holding since the last great ice sheets formed. If the Younger Dryas was the sharp gasp of a world thrown back into winter, then the end of it, between 11,700 and 11,600 years ago, was the exhale. A deep planetary release. A return to warmth so rapid that even in the language of geology it reads like a jolt. And if you could have stood on the tundra during those extraordinary centuries, you might have asked yourself a strange question. What does a planet sound like when it wakes up all at once? To understand this moment, we must look again into the frozen memories of Greenland. The ice cores from this region show something astonishing. At the end of the Younger Dryas, temperatures did not simply rise, they surged. Within a span that may have been no more than a few human generations, the climate shifted from near glacial conditions into something resembling the warmer, more stable Holocene world we know today. In the isotope record, this transition is visible as a steep upward curve, a line on a graph that climbs so abruptly it almost seems out of place among the slow, rhythmic waves of earlier millennia. Scientists sometimes describe this change as a climate termination, a word that captures both the suddenness and the finality of what happened. The reveal hidden in this data is that the end of the Younger Dryas was not a slow recovery. It was a rapid transformation. Dust levels in the ice cores fall sharply, indicating that winds weakened and moisture returned to the atmosphere. Methane concentrations rise, a sign that wetlands, long subdued by cold, were expanding once again. The chemistry of ancient bubbles tells a story of a world shifting gears. Something in the Earth system changed abruptly and decisively, pushing the planet out of the longer glacial rhythm that had defined tens of thousands of years. What triggered this extraordinary thaw? The most widely supported explanation again involves the oceans. As the Younger Dryas progressed, the fresh water that had disrupted the Atlantic circulation began to diminish. Over time, the great ocean conveyor belt recovered its strength. Warm currents flowed northward once more, delivering heat to the higher latitudes and breaking the cold's hold on the continents. But the system did not simply return to its previous state. It seems to have overcorrected, releasing a cascade of warming that spread rapidly through the northern hemisphere. The evidence for this recovery lies not only in ice, but in ancient sediments. Pollen from lake cores shifts once again, this time away from tundra grasses and back toward shrubs and trees. Within just a few centuries, species of birch and pine reclaim vast territories they had been forced to abandon. Forests march northward, following the retreating cold in patterns so swift that botanists studying these transitions often describe them as explosive. Animals adapted to open, frozen landscapes find themselves moving through increasingly wooded environments. The ecological map changes with surprising speed. Glaciers, too, respond dramatically to this warming. The great ice sheets that had stabilized during the Younger Dryas begin to shrink rapidly. Their margins recede. Meltwater streams carve deeper pathways across the land. The soundscape of the world changes, cracking ice, flowing water, shifting sediment. When temperatures rise this quickly, ice does not melt quietly. It fractures, collapses, and gives way with a force that echoes across valleys and plains. The retreat of ice is written into the land, visible in moraines and meltwater channels still present today. Atmospheric markers reinforce this picture. Greenhouse gas concentrations rise, perhaps as thawing wetlands release methane trapped during colder centuries. Changes in wind patterns appear in the grain size of windblown sediments, which become finer as the climate becomes warmer and wetter. Even cave formations respond. Stalagmites in distant regions show changes in oxygen isotopes that match the abrupt shift in global circulation. Everything that archives climate, ice, sediment, plants, water, stone, seems to pivot at nearly the same moment. What if you were living then? You would not have seen the graphs. You would not have known that temperature curves were bending upwards so sharply they would one day reshape the entire Holocene. But you would have felt the thaw. The winters would begin to soften. Springs would arrive earlier. Lakes that had frozen deeply each year might thaw sooner and remain open longer. The air would hold more moisture. Fog might form in valleys that had rarely seen it before. Animals that had been scarce in colder decades might return to familiar ranges. The world would feel as though it were breathing again. And yet, even with this sensory understanding, the actual speed of the transition would be beyond any human interpretation. People experience seasons, not isotopes. They remember lifetimes, not millennia. What the planet did between 11,700 and 11,600 years ago is something that only the geological record can reveal in its full magnitude. A climate that had been balanced on the edge of cold suddenly tipped toward warmth. And remarkably, this warming did not reverse. It became the foundation for the entire Holocene, the epoch in which all recorded human history would eventually unfold. One of the quiet revelations of this period lies in how ecosystems reorganize themselves. The expansion of forests did not occur gently. It happened in pulses, driven by both climate and the biological momentum of returning species. Tree lines advanced northward at rates far faster than their long-term averages. Nutrient cycles accelerated as soils thawed and decomposers regained active roles in the ecosystem. Rivers, freed from seasonal ice, began cutting new paths into the warming ground. Lakes expanded or contracted depending on rainfall patterns, which no longer followed the tightly constrained rhythms of younger Dryas climate. Wetlands spread across low-lying regions, bringing with them the sounds of birds and the hum of insects that had been absent during colder centuries. Climate models offer another insight. They suggest that the end of the younger Dryas may have been associated with shifts in the position of the jet stream. As temperatures rose, atmospheric circulation patterns reorganized. Storm tracks changed, precipitation redistributed. Some regions grew wetter, others drier. The transition was not uniform, but its direction was unmistakable. The world was moving toward a warmer, more stable state. What makes this event so extraordinary is that it marks the final boundary between two worlds. On one side lies the Pleistocene, an era defined by cycles of glaciation, abrupt climate swings, and ecosystems built for cold endurance. On the other lies the Holocene, a comparatively warm and stable period during which humans would eventually settle, cultivate, build, and reshape landscapes. The line between these eras is drawn sharply in the ice cores. It is written in the temperature curve with the precision of a geological signature. But the transition itself is not a deliberate story. It is a cascade of feedback loops within the climate system. Ice melts, albedo decreases, the planet absorbs more heat, and warming accelerates. Oceans circulate differently, redistributing warmth. Vegetation expands, affecting carbon cycles. The system moves toward a new equilibrium, and once that new state is reached, it holds for thousands of years. If we step back, we can see the scale of what happened in those few centuries at the end of the younger Dryas. An entire climate mode collapsed. An ice age that had defined the shape of continents withdrew. Life reorganized itself. The planet entered a new chapter, not because of any external command, but because its own internal systems regained balance. This is the quiet truth of the Earth. Its transformations are often abrupt, but they are always interconnected. The end of the younger Dryas is one of the clearest examples of this interconnectedness. It is a reminder that climate is not a distant, slow-moving background force. It is active, sensitive, and capable of abrupt shifts that reverberate through ecosystems and across continents. Even without speaking of the events that followed, we can appreciate this moment for what it is, the doorway through which the modern world entered. Today, when we look at the graphs, the sediments, the isotopes, and the fossils, we are reading a story the world wrote when it thawed for the final time. And although there is still debate about some of the triggering mechanisms, the overall picture is clear. The younger Dryas ended abruptly. The final thaw was rapid, and the planet moved into a climate that would shape everything that came after. What does a planet sound like when it wakes up all at once? Perhaps it sounds like the cracking of ancient ice, like the return of water running freely after centuries of cold, like forests growing where there had been none. Or perhaps it sounds like nothing at all, a shift so vast, so global, that the only voices that could hear it were the sediments, the ice, and the air, waiting to be trapped in bubbles for us to find millennia later. You're standing at the edge of a continent made of ice, not a glacier the size of a mountain valley, not a frozen river, but an entire world of white stretching for thousands of miles. The wall in front of you is nearly 2 miles thick. It rises like a cliff carved by no human hand, its face blue and ancient, its weight pressing down on the very crust of the earth. For thousands upon thousands of years it has been unmoving, a monument of cold. And then, in the narrow window between 11,700 and 11,600 years ago, it begins to break. Not gently, not quietly, but with a deep structural failure that starts inside the ice, long before anyone could see it. What breaks first when 2-mile-thick ice walls begin to fail? That is the story written in the scars of continents. To understand how these enormous ice sheets collapsed, we have to look inside them. An ice sheet is not a solid block. It is layered snowfall compressed over tens of thousands of winters. Each year adds another thin sheet, another memory trapped in cold. Over time, the weight becomes almost unimaginable. In the deepest parts of the North American Laurentide ice sheet, pressure from the ice above fused crystals together until the lower layers behaved like a slow-moving plastic. The entire structure was held together by cold. It was a frozen architecture of ancient storms. But as the younger Dryas ended, warmth infiltrated the surface, seeped into cracks, pooled in depressions, and created thin veins of liquid water that began the process of structural weakening. The reveal hidden inside this warming is simple. Ice breaks from within long before it breaks at the surface. When temperatures rose rapidly at the end of the younger Dryas, meltwater formed on top of the ice sheets. These pools were not shallow puddles. Some were lakes miles across, gathering in basins where the ice sagged under its own weight. And when water sits on ice, it begins to find pathways. Even a tiny crack is enough. Water flows downward with gravity, widening fractures as it moves, carving shafts known as moulins. Once water reaches the base of a glacier or ice sheet, it acts like a lubricant, reducing friction and allowing the ice above to slide forward more easily. This sliding destabilized the footing of entire ice masses. The mechanical behavior of ice is a lesson in patience and thresholds. Cold ice is rigid. Warm ice is ductile. As temperatures rose, large portions of the ice sheets crossed a threshold where internal deformation increased dramatically. The deep ice began to flow faster toward the margins. The surface cracked under stress. Crevasses opened in places that had been stable for millennia. Icebergs carved not only at ocean faces but also along interior fractures where the ice had become too thin to support its weight. A world that once moved inches per year began moving feet per day in some regions. Still slow compared to human motion, but astonishing for structures so massive. The next piece of this story lies in the lakes that formed along the edges of the melting ice. As the ice sheets retreated, they left behind enormous depressions carved into the land. These depressions filled with meltwater, forming lakes that dwarfed anything in our modern world. One of the largest, often referred to by scientists as Glacial Lake Agassiz, expanded across regions that today span multiple countries. Another formed in what is now the interior of Europe, trapped between ice and rising land. These lakes were held in place by ice dams, natural barriers made not of rock, but of compressed snow and frozen water. Ice dams look solid. They feel immense, but they are fragile. They melt from above in the sun. They melt from below as warm water pools against them, and they fail when fractures widen enough for water to find a path through. Once water begins to flow through a crack, erosion accelerates. The meltwater cuts channels deeper and deeper, enlarging the flow. Eventually the dam gives way. The vast lakes behind them are released in catastrophic drainage events. These outbursts are not gentle trickles. They are violent, sudden, and reshaping. Entire landscapes bear the marks of these failures. To picture the moment an ice dam fails, Imagine a wall of frozen water holding back a lake larger than all modern Great Lakes combined. Now imagine the first small breach opening. Water begins to pour through, the pressure increases, the ice fractures, and in a matter of days or hours the entire structure collapses. What was once a stable barrier becomes a channel. The lake drains rapidly, leaving behind scoured valleys, giant boulders carried for miles, and sediments piled in ridges. These features still exist today as evidence of the glacial mechanics that shaped the late Pleistocene. But not all collapses were dramatic. Some were quiet. As the ice sheets thinned, their centres sagged. Stress built up in the interior, creating deep fractures. The once flat surfaces warped. When ice becomes thin enough, it can no longer withstand the tension from its own flow. It stretches and breaks. Large sections detach and move independently, forming ice streams, fast-moving corridors of ice that act like conveyor belts within the larger sheet. These ice streams drained enormous volumes of ice from the interior, accelerating collapse in ways invisible to anyone living on the ground at the time. Another factor in this continental melt was the bed beneath the ice. The underlying geology of North America and Europe influenced how the ice behaved. Some regions rested on soft sediments that deformed under pressure. Others lay atop hard bedrock. Where the bed was soft, the ice sheet slid more easily. Where the bedrock was uneven, meltwater pooled in depressions and carved subglacial channels. These channels became rivers beneath the ice, transporting water across vast distances and shaping the collapse from below. Subglacial water networks are one of the least visible but most important forces in glacial dynamics. The Earth's crust also played a role. For tens of thousands of years, the ice sheets had pressed the land downward. As the ice melted, the land began to rise in a process called isostatic rebound. This uplift was not uniform. Some parts of the crust rose faster than others. This uneven rebound changed the tilt of the land surface, redirecting meltwater flows and altering the stability of ice margins. Lakes drained in new directions. Rivers shifted. The entire hydrological system reorganized itself in response to the lifting of the crust. The atmosphere recorded this transformation as well. Dust levels changed as retreating ice exposed new sediments to wind. Moisture increased as ice-free oceans warmed and fed the air with water vapor. Temperature curves from ice cores show a stabilization into the warmer conditions characteristic of the Holocene. The planet was locking into a new climate state, one without the massive glacial engines that had dominated the Pleistocene. And once these engines failed, they could not easily reform. The ice sheets collapsed not only because they melted, but because the entire climate system had moved beyond the thresholds needed to sustain them. If you imagine yourself standing near the edge of the Laurentide or the Scandinavian ice sheets during these centuries, you might have heard sounds no human language could fully describe. The deep thunder of ice cracking, the rush of meltwater carving new canyons, the groaning of entire ice masses shifting under their own weight. From a distance it may have sounded like distant storms. Up close it would have felt like the Earth itself was moving. And yet, despite all of this power, the mechanics of a continental melt are governed by simple physics. Temperature, pressure, gravity, and water. Raise the temperature beyond a threshold and ice deforms. Add meltwater and ice slides. Remove the structural support of thick layers and fractures propagate. Warm the oceans and the margins weaken. A glacier is not static. It is a system that responds to every small imbalance. And during these extraordinary centuries, imbalance became the norm. The collapse of the ice sheets marks the true end of the Ice Age. By 11,600 years ago, the great frozen monuments that had shaped continents for tens of thousands of years were withdrawing, thinning, and breaking apart. Their remnants would survive in smaller forms, Greenland, Antarctica, but the age of continental ice was over. The planet had shifted into a new climate rhythm, one that would allow ecosystems to flourish in ways impossible under the heavy weight of ice. What remains of the ice sheets today are not their towering walls, but the landscapes they carved. Moraines outlining their former boundaries, lakes that filled their empty basins, smoothed bedrock left behind by their grinding movement, valleys carved by meltwater rivers. These features a geological memory, the silent record of a world that melted from the inside out. When we study these features now, we do so with humility. The collapse of the ice sheets was not the result of a single cause. It was the culmination of many interacting processes: mechanical, climatic, hydrological, and geological. The science is still evolving. We still debate the timing of certain collapses, the volumes of meltwater lakes, the precise flow paths beneath the ice. But the broad picture is clear. When warmth returned at the end of the younger Dryas, the ice sheets crossed irreversible thresholds. They fractured, they drained, they slid. And in doing so, they reshaped the world that would soon become home to the first complex human societies. What breaks first when 2-mile-thick ice walls begin to fail? Everything that warmth can reach. You're standing on a shoreline you've known your entire life. The tide comes in, the tide goes out. It has done so for thousands upon thousands of years. And then one season something feels different. The water returns a little higher, a little deeper, not enough to alarm you at first, but enough that if you watch the shoreline carefully, day after day, you might start to wonder, can the ocean rise faster than a human can walk? To us, this sounds almost impossible. Oceans are ancient, heavy things. They move slowly. They breathe in geological rhythms. Yet around 11,600 years ago, during what scientists call meltwater pulse 1A, our planet proved that even seas can jump. To understand this extraordinary moment, we must return to the simplest evidence we have: coral. Corals do not grow sideways. They grow upward towards sunlight, and when the ocean around them rises, they grow faster to keep pace. That growth becomes a record. Layer by layer, year by year, corals build a vertical diary of changing sea levels. When scientists drill into ancient coral terraces in places like Tahiti or Barbados, they can read this diary with astonishing resolution. And what it tells us about the end of the Ice Age is astonishing in return. The coral records show a period where the ocean rose so quickly that reefs struggled to keep up. Their growth rates accelerate sharply. It is as if the ocean floor beneath them began to sink, but the truth is the opposite. The surface of the sea was rising. According to these corals, global sea levels may have climbed many tens of feet within a short span of centuries. Some models even suggest that parts of this rise happened within decades. Not enough to watch the water climbing day by day, but enough that one lifetime could notice the shoreline retreating. Enough that the sea might advance faster than seasonal memory could adjust. The reveal inside this data is simple. Meltwater pulse 1A was not a slow melt, it was a surge. But how do we know the timing is real? This is where the sediment cores provide a second line of evidence. Beneath the oceans lie thick layers of mud, sand, shells, and microfossils. These layers accumulate slowly, like the pages of an ancient book. The deeper you drill, the older the story. And inside these stories, scientists find dramatic changes in the composition of marine sediments around the time of meltwater pulse 1A. In some cores, tiny shells from deep-sea organisms suddenly appear at shallower depths, indicating a rapid flooding of continental shelves. In others, layers of sand show up where only mud should be, evidence of shoreline movements that reshaped coastal ecosystems within a few centuries. These geological signatures confirm that the oceans expanded quickly, and they align with the coral records almost perfectly. When two separate archives of Earth's memory tell the same story, we must pay attention. To understand how this happened, we must return to the ice. At the end of the Younger Dryas, as warmth surged across the northern hemisphere, the massive ice sheets that once covered North America and northern Europe weakened to the point of structural collapse. As their walls fractured, as lakes drained, and as ice began to slide more easily across the land beneath it, enormous volumes of water were released, not in one global burst, but in multiple regional flows that eventually reached the oceans. These flows fed into meltwater, Pulse 1a, a planetary expression of all the ice that no longer had the strength to remain frozen. The numbers behind these changes are staggering. By the time meltwater Pulse 1a had run its course, global sea levels had climbed enough to redraw the map of the world. Coastlines retreated far inland. Islands emerged where hills once were. Shallow seas formed over what used to be plains. The shape of continents changed. River mouths migrated. Ocean circulation shifted. Although we cannot mention the human dimension here, we can say with certainty, Earth's geography itself transformed. One of the most compelling aspects of meltwater Pulse 1a is its speed. Geologists often speak of rapid changes, but rapid in geological terms usually means thousands of years. Meltwater Pulse 1a defies that pacing. It suggests that Earth is capable of making massive adjustments on timescales close to human experience. The coral terraces that record these changes sometimes show jumps that could represent only a handful of decades. This does not mean oceans rose feet per year everywhere, but it does mean that the long-term average during this pulse was extraordinary compared to the rest of the late Pleistocene. If we look to climate models for explanation, they suggest that the collapse of the great ice sheets released meltwater at rates far beyond anything produced by ordinary seasonal melt. As the ice thinned, its ability to maintain stable margins weakened. Calving increased. Meltwater lakes breached. Ice streams accelerated. All these processes combined to send massive quantities of water toward the oceans. Once the water reached the coast, the ocean had no choice but to rise. Another clue lies in the isotopic composition of ocean sediments. When ice melts and enters the sea, it changes the ratio of oxygen isotopes in seawater. These isotopes become part of the shells of tiny ocean organisms. By studying those shells, scientists can trace the timing and volume of meltwater entering the ocean. Around 11,600 years ago, these isotopes signal a dramatic shift toward lighter water, characteristic of glacial melt. This shift is consistent with the coral evidence and further supports the idea of a sudden influx of fresh water. It is also important to understand that the rise was not uniform worldwide. Some regions experienced greater changes than others due to local geological uplift or subsidence. But the global average rise was unmistakable. Coral reefs drowned, coastal plains disappeared, lagoons became bays, fjords expanded as ice retreated inland. The ocean surface lifted like a slow tide that never turned back. If you stood on a shoreline during this time and watched the horizon carefully, the change would be too slow to see moment by moment. But over years, maybe decades, you would begin to notice something unsettling. A familiar rock where birds nested may have disappeared beneath the waves. A piece of land used for gathering plants might now be marshy or submerged. Perhaps a river mouth shifted, its flow redirected by rising water. The world would not feel like it was ending. It would feel like it was moving. One of the quiet truths of Meltwater Pulse 1a is that the Earth had been holding this water for tens of thousands of years, locked in ice, pressed into glaciers, stored high above sea level. When the final warming came, the release was unstoppable. The oceans became the basin into which all this ancient water returned, and once the oceans rose, there was no mechanism to send the water back. The Ice Age machinery had shut down. The world had moved into a new climate phase. What remains today are the clues left behind. Coral terraces standing above modern shorelines, relics of ancient seas, submerged sand dunes deep beneath the ocean, layers of marine sediments marking sudden environmental transitions, bathymetric maps showing continental shelves carved by rising waters. All these pieces form a puzzle that scientists have assembled over decades of research, each study refining our understanding of how quickly the world can transform. And yet, despite all this evidence, many details remain uncertain. How much water came from North America versus Europe? How many separate pulses contributed to the overall rise? Were there variations in timing between different ocean basins? These questions remind us that the geological record, while faithful, is not perfect. It requires interpretation, it requires humility, and it requires understanding that Earth rarely gives us a complete picture all at once. What we can say with confidence is that meltwater pulse 1A represents one of the fastest large-scale sea level rises in Earth's recent history. It marks the true beginning of the Holocene world, a planet with far less ice, far more water, and coastlines that resemble the shapes we know today. The transition was neither gentle nor slow. It was a reminder that even the most ancient and stable parts of our world, the oceans themselves, can shift with astonishing speed when the climate crosses certain thresholds. Can the ocean rise faster than a human can walk? Not in a single day, but in a lifetime? In these centuries at the end of the Ice Age, the answer may have been yes. The world you know has coastlines, familiar curves where water meets land, where waves break, where the horizon feels fixed. Now imagine pulling back the oceans by 400 feet. Imagine peeling the seas away like a veil and exposing a planet you've never seen before. Between 20,000 and 12,000 years ago, the Earth looked nothing like the world mapped in our books. Entire continents were larger. Land bridges connected regions we now think of as islands. Shelves of dry grassland spread across what is today ocean floor. If you could walk across that earlier world, you would cross landscapes that no longer exist. And the quiet truth is that most of our deep human story, our migrations, our settlements, our paths, took place on land now lost beneath the sea. What vanished when the shorelines we know disappeared under 400 feet of water? To reconstruct this vanished geography, we turn first to bathymetry, the underwater equivalent of topographic mapping. Bathymetric surveys use sonar to map the seafloor, revealing ridges, valleys, plains, and continental shelves that once lay above the ocean. When scientists combine these maps with precise measurements of past sea levels, a different Earth emerges. A world where the edges of continents protruded far beyond their modern boundaries, exposing vast regions of land that were fertile, habitable, and central to the lives of early humans. One of the most striking features of this earlier world is the sheer size of the exposed continental shelves. Today, the shelves lie hidden beneath shallow seas, supporting marine life but concealing their former identity as plains. In the last glacial maximum around 20,000 years ago, sea levels were so low that these shelves formed continuous strips of dry land around continents. Some of them were hundreds of miles wide. Walk across them then, and you would find yourself on expansive grasslands, dotted with wetlands, river networks, and roaming animals. These were not barren peripheries, they were ecosystems in their own right. The reveal in the data is that our modern shorelines are temporary features, They are simply the current meeting point between land and water. For most of human prehistory, the boundaries were different. The Earth in this period was a planet where Asia and North America were connected by a broad stretch of land known today as Beringia. This land bridge was not a narrow passage. It was a continent-sized region, cold, windy, but rich with grasses and animals. Herds of mammoths, horses and bison crossed this region. Predators followed. Humans did too. Beringia was a bridge, but more importantly it was a world between worlds, a living space that no longer exists. Elsewhere, the shallow seas between Southeast Asian islands were dry plains. The archipelagos we see on maps, Indonesia, Malaysia, the Philippines, were connected by land. Scientists call this combined region Sundaland. During the late Pleistocene, Sundaland was nearly the size of modern Europe. It held tropical forests, river deltas and interior highlands. It connected people and animals in ways that the later rising seas would erase. Today we see islands. But back then, humans walked across continuous landscapes. Farther west, another massive landmass existed, Sahel. This connected what we now call Australia to New Guinea and Tasmania. Instead of separate islands, they formed a single continent with continuous ecosystems. Animals moved freely. Humans, already present for tens of thousands of years, inhabited this united land long before ocean channels divided it. Europe too looked different from today. The North Sea basin, now filled with cold water and dotted with oil rigs, was once a low-lying plain rich with rivers, lakes, marshlands and forests. This region connected Britain to continental Europe. If you were alive 12 or 15,000 years ago, you could walk from what is now Germany to what is now England without ever seeing the ocean. Today we call this submerged region the North Sea Shelf, but in its time it was an enormous stretch of land supporting animals, plants and people. Even the Mediterranean looked different. Its sea level was lower, exposing coastal plains and reshaping islands into peninsulas. The geography of Greece was especially transformed. Coastlines stretched farther outward. Islands like Crete were closer to the mainland, and the Aegean was scattered with land bridges that vanished once the water rose. How do we know these landscapes existed? Part of the answer comes from GIS models, three-dimensional reconstructions that combine sea level curves with digital elevation data. When scientists input sea levels from 20,000, 15,000 or 12,000 years ago, these models reveal the extent of land loss. The process is almost like draining the oceans inside a computer simulation. With each metre of sea level removed, more of the Earth is exposed. When the models reach the low sea levels of the late Pleistocene, enormous regions reappear. Another line of evidence comes from rivers. Ancient river channels can still be traced on the seafloor. Sonar scans show winding paths carved into what is now underwater sediment. These channels are too large to have formed beneath the ocean. They were created when the land was exposed. Some flowed hundreds of miles across the continental shelves, carrying water from inland springs to the distant coastlines of that earlier world. The shape of these ancient rivers confirms that the submerged plains were once thriving landscapes. The vanished coastlines were not empty. They were home to grasslands, forests, wetlands, and rich coastal ecosystems. Animals followed the vegetation. Nourished by rivers, lake systems, and seasonal rains, the continental shelves were abundant feeding grounds. Herds migrated across them. Predators stalked these open landscapes. Birds nested in wetlands. And although we will not speak here about specific human settlements or cultural memory, we can say that any creature living near the edges of continents lived in a world much larger than ours. The distribution of wind-blown sediments also hints at the shape of these lost lands. Dunes found beneath shallow waters suggest that some regions of the continental shelves were dry enough for desert-like conditions to form. In other places, peat deposits buried under marine sediments indicate that wetlands once covered these areas. The Earth's own geology preserves snapshots of environments that are now hidden. When we reconstruct this earlier world, something remarkable emerges. The map of Earth, around 20,000 to 12,000 years ago, shows a planet with much greater land area. The continents had wider edges. The islands we know today were highlands then. The relationship between land and water was different in almost every region. The world of that time feels familiar, but enlarged, like a version of Earth with the seas pulled back just enough to reveal the full extent of its continental bones. Imagine walking across the western edge of the European shelf during one of the warm interludes. You might see rolling hills stretching far beyond where modern coastlines lie. Rivers would wind toward the distant ocean, their banks lined with grasses. Herds of herbivores might graze along extended plains. In the far distance, where now the waves break over sand and stone, you would see the line of the ancient shoreline much farther out. The place where water met land would have felt stable, timeless. But stability was an illusion. When the ice sheets began to melt more rapidly, that shoreline journeyed inland, erasing all traces of the vast plains beneath it. This is perhaps the most humbling part of the reconstruction. The realization that much of human prehistory occurred on land that no longer exists above water. Entire landscapes that shaped migrations, hunting strategies and ecosystems have been erased by rising seas. When we look at maps today, we see only the final stage of a long geological transformation. The earlier stages lie beneath hundreds of feet of water. Geologists often describe the continental shelves as archives. Their sediments preserve pollen from ancient plants, bones from animals that grazed their plains, and erosion patterns that reveal the climate conditions of the time. These shelves are not merely underwater extensions of land. They are lost chapters of the Earth's surface. They hold clues to how climates fluctuated, how ecosystems evolved, and how the world reorganized itself after each glacial cycle. If we step back and imagine the Earth before the flood, we see not a fringe of land hugging the oceans, but a vast interconnected world. Asia connected to North America, Australia connected to New Guinea, Europe connected to the British Isles. The islands of Southeast Asia fused into a single landmass. Coastlines stretched outward for miles. Plains spread across regions where today only waves move. The resolution of this reconstruction is simple and profound. The Earth we inhabit is the survivor of a flooded world. Its shorelines are not ancient. They are young, shaped within the last 10,000 years. Beneath the surface of the oceans lies the geography of an older planet, a planet where early humans lived, walked, hunted, and adapted. And although those landscapes are lost to the water, their outlines remain in the quiet topography of the seafloor, waiting for us to read them. Imagine this. You wake up to the sound of waves. Not a distant roar, not the echo of a storm, but the steady rhythmic pulse of a living boundary. For the people who lived between 15,000 and 12,000 years ago, the coastline was not scenery. It was not a line on a map. It was a source of food, a pathway through the seasons, a library of tides, shells, birds and winds that carried meaning long before writing existed. To live on the edge of land and sea was to live inside a system older than memory. And if you had asked someone then what a coastline meant, they would not have spoken of real estate or borders. They would have spoken of hunger, movement, skill, and the quiet understanding that everything depended on reading the water correctly. To understand these people, we must first understand their world. The coastlines of 15,000 years ago were not the coastlines we know today. The sea sat far lower. Bays were wider. Rivers flowed across plains now underwater. Beaches stretched for miles. Tidal flats were immense feeding grounds. Kelp forests hugged the edges of continents. And above all of this, humans lived in small groups that moved with the seasons, following resources that appeared and disappeared in predictable rhythms. The reveal beneath this history is that coastal hunter-gatherers were not wanderers without knowledge. They were precisely the opposite. They built their lives around the reliability of the ocean. They understood that the sea is generous, but only to those who learn its habits. Their tools, camps, and strategies reflect a deep intimacy with marine environments, a relationship shaped through thousands of years of observation. One of the clearest expressions of this relationship comes from shell middens. A shell midden is not a random pile of discarded shells. It is a monument of meals layered slowly over generations. When archaeologists examine these middens, they see the remains of oysters, clams, mussels, limpets, fish bones, bird bones, charcoal, and broken tools. What these layers show is a long-term commitment to the coast. People return to the same places year after year. The size and thickness of middens indicate repeated use, often over centuries. They reveal seasonal patterns, species harvested in winter versus summer, fish caught during spawning runs, birds taken during migrations. Through these middens we can trace the rhythms of ancient coastal life. Fishing was another pillar of survival. Nets, hooks, harpoons, fish traps, and weirs reflect sophisticated understanding of marine behaviour. Long before agriculture, long before boats crossed distant seas, humans built traps that harnessed tides. They placed stone walls in intertidal zones, creating enclosures that filled with fish as the tide rose and left them stranded as the tide fell. These structures required knowledge of lunar cycles, tidal timing, seasonal fish movements, and shoreline topography. They also required a kind of quiet engineering rarely associated with Pleistocene people. Beyond fishing, there was gathering. Coastal ecosystems are layered with edible plants, shellfish, crustaceans, seaweed, and bird eggs. These foods were predictable and renewable. A knowledgeable forager could walk a shoreline and fill a basket quickly, selecting only the safe, edible, and nourishing. Such knowledge was inherited through generations, carried not in writing but in memory, stories, and practice. Hunting also played a role. Shorebirds, seals, sea lions, and coastal ungulates offered meat and fat. Migratory birds followed ancient flyways along the coasts, providing seasonal abundance. Hunters built blinds from reeds and driftwood. They fashioned barbed points for marine mammals. They learned how wind carried scent over water and how birds behaved before storms. This was not random hunting. It was skilled, patient, and deeply tied to reading the edge where land meets sea. But what truly defines coastal hunter-gatherers of this time is mobility. Their camps were seasonal. In warmer months, groups often moved closer to exposed beaches, where fish and shellfish were abundant. In colder months, they might retreat slightly inland, following rivers or sheltered forests where game was easier to find. These movements created coastal migration corridors, routes shaped not by exploration but by ecological timing. People moved because the resources moved, and the resources moved because the ocean moved. Interestingly, many of these corridors aligned with regions that would later disappear beneath rising seas. People lived on floodplains that no longer exist. They harvested shellfish from beaches now hundreds of feet underwater. They walked across coastal plains now mapped only through sonar. And although we will not speak here of their memories of later events, we can say that their world was built on landscapes that are now hidden. One of the least understood aspects of coastal life is how people navigated alongshore travel. We often imagine early humans as inland walkers, but coastlines offered some of the easiest routes for movement. The land was flat, water was abundant, food was predictable, driftwood provided materials for tools, kelp forests stabilised marine ecosystems, offering natural harbours. Even without speaking of boats, we know that many coastal groups likely use simple watercraft, rafts, dugouts, skin boats to extend their range. Evidence from genetics, tool distribution, and ecological modelling suggests that coastal mobility was one of the most efficient ways humans spread across continents. Beyond movement, coastlines provided something else: stability in an unstable climate. While ice sheets advanced and retreated inland, the coasts offered consistent sources of food. When tundra gave way to forest, when herds shifted north or south, the ocean remained a constant. Fish swam, shellfish grew, birds nested. For people living through the dramatic climate changes of 15,000 to 12,000 years ago, the coast may have been the most reliable environment they knew. One of the quiet insights of coastal archaeology is how much of human cultural development happened near water. Many of the earliest ornament traditions, shell beads, fishbone tools, carved objects, come from coastal sites. This is not surprising. Shells are durable, fishbones are workable, driftwood floats into creativity, and the rhythm of tides invites reflection, craft, and routine. The coast is not only a place of survival, it is a place of culture. We also see evidence of social networks along the coasts. Certain types of stone tools found hundreds of miles apart imply long-distance exchange. Beads made from marine shells appear far inland, suggesting trade routes or seasonal journeys. These connections remind us that coastal life was not isolated. The people who lived there were part of regional webs of travel, sharing, and knowledge. A shell bead found far from the ocean carries with it the echo of a shoreline, where someone picked it up, shaped it, wore it, and eventually passed it into a world beyond the coast. Imagine yourself walking across one of these ancient beaches. The sand beneath your feet is not the sand of modern coastlines. It is coarser, full of broken shell fragments and driftwood. To your left, the ocean glistens in early light. Birds circle overhead. In the shallows, schools of fish flicker like silver mirrors. To your right, inland, a line of low dunes leads to forests or river valleys. Somewhere behind those dunes is a seasonal camp. Hearth rings, fish racks, piles of gathered shells, sleeping sites lined with grasses. The camp is temporary, but it carries memories and habits. People return not because they must, but because they know it works. As the day progresses, you watch the tide withdraw, revealing tidal flats rich with shellfish. The group moves across the exposed mud, stopping to gather food. Children join, learning which shells are safe, which to avoid, and how to pry them gently without damaging the next generation. Later, you might see hunters return with fish caught in traps or speared from the shallows. The work is constant but patterned. Nothing is wasted. Nothing is guessed. Everything follows a rhythm the sea teaches. This is what the coastline meant: knowledge, pattern, return. If we step back from the details and observe the larger picture, we see a world tied together by edges. People across continents develop similar strategies because coastlines demand similar responses. The ocean rewards those who understand its timing, its behaviour, its generosity. The techniques varied. Nets here, traps there, shell gathering in one region, kelp harvesting in another. But the underlying logic remained the same. The Earth between 15,000 and 12,000 years ago was changing. Ice sheets were melting. Ecosystems were shifting. but the coast remained a constant meeting place, a place where land and sea shaped each other, a place where early humans built lives around consistency in a world of instability. What does a coastline mean to a people whose entire life depends on it? It means orientation. It means survival. It means belonging to the boundary where two worlds meet and learning to live with both. Imagine this. One season you return to a familiar shoreline and something is wrong. The tide sits a little higher. The beach where you gathered shellfish is narrower. A cluster of driftwood that marked the edge of the last year's camp now lies half buried in wet sand. Nothing dramatic has happened. There is no storm, no roar, no sudden wall of water. And yet, the horizon has shifted. The edge of the world has stepped closer. For the people living between 13,000 and 11,600 years ago, this was the nature of change. Not a single event, but a quiet rearrangement of the planet. So slow it could be ignored, yet so steady it could not be stopped. How do you adapt when the horizon moves closer every season? To answer that, we have to imagine a world where sea levels did not feel fixed. For thousands of years before agriculture, long before permanent villages or brick walls or written records, hunter-gatherer communities lived in landscapes shaped by water. They followed rivers, camped at estuaries, harvested tidal flats, and moved with seasonal abundance. When the Ice Age began to break, when glaciers melted far inland, the water they released flowed outward into the oceans. But the rise was not a sudden surge. It was a slow, incremental climb that played out across centuries. For a single lifetime, the change was subtle. For several lifetimes in a row, it became unmistakable. The archaeological record tells this story not through written sources, there were none, but through absences, places where camps once stood and then faded, layers of tools and hearths overlain by younger sediments that lie closer and closer to the modern shoreline, patterns of inland movement visible in the geographic spread of sites. To reconstruct this movement, archaeologists look at where settlements appear, when they appear, and how long they were used. When a coastline retreats inland, the sites closest to the water disappear from the archaeological landscape. Camp by camp, generation by generation, the record shifts. The reveal hidden in this evidence is that people were not passive. They adapted. They moved their camps. They changed where they gathered food. They reorganized their seasonal paths. The rising sea did not erase their world overnight. It nudged them, season after season, into new patterns of life. One of the clearest indicators of this change is the spatial drift of coastal sites. In regions where sea levels rose steadily through the late Pleistocene and early Holocene, early human camps cluster farther inland over time. At the beginning of this window, around 13,000 years ago, many camps sit relatively close to paleo shorelines that no longer exist. By 12,000 years ago, new sites appear farther inward, built in areas that would once have been too distant from tidal food sources. Archaeologists map these shifts using radiocarbon dates, tool types, hearth remains, and environmental analyses of sediments. When plotted together, they form a trail, a human response to a world slowly drowning its lowest edges. In some regions, the movement inland appears gradual. A site used for centuries becomes too damp, or too far from shifting fish migrations, or too vulnerable to encroaching tides. Families stop returning. They establish a new camp slightly farther inland, perhaps near a freshwater spring or sheltered valley. Over generations, this becomes the new normal. To us, this looks like environmental displacement. To them, it may have looked like simple adaptation, another shift in a world where landscapes always changed. One reason communities were able to respond is that their mobility was built into their way of life. Hunter-gatherers did not anchor themselves to permanent structures. Their homes were portable, their tools were light, their knowledge systems were flexible. When a shoreline changed, they changed with it. A path that once led to a clam bed might now lead to shallow marsh. A trail toward a fishing ground might shift with the river feeding it. Movement was an adaptation long before it became a necessity. Ecology played a role as well. As the sea rose, the distribution of coastal resources changed. Species that depended on shallow water, shellfish, seaweeds, certain fish, shifted landward with the shoreline. Birds followed the changing edge. Freshwater systems expanded in some areas and contracted in others. The balance between saltwater and freshwater environments created patches of abundance and scarcity. People learned where those patches moved. We see traces of this in the types of tools left behind. In earlier layers, we find fishhooks and harpoons designed for deeper or more distant waters. In later layers, as the coastline moved, the tools shift toward harvesting species that thrived in new shallow environments. Fish that followed the tide inland. Shellfish that colonized changing tidal flats. The toolkits changed because the ecosystem changed. The gradual movement inland also appears in hearths and cooking remains. In many coastal regions, the composition of hearth ash shifts from saltwater species to freshwater species over thousands of years. This tells us that people followed rivers inland as their mouths migrated. Fish that once swam in estuaries now swam farther upstream. Plants that once grew near the coast began to grow farther inland. The hearth fire is one of the most honest witnesses to environmental change. But perhaps the most subtle evidence of human response comes from the way camps were built. In some regions, early camps sit on low terraces just above the ancient shoreline. As sea levels rise, later camps appear on higher terraces, geological steps left behind by rivers or glaciers. These terraces offered protection from tides and storms. Over time, groups seem to have preferred sites with greater elevation and better drainage. The choice reflects a quiet awareness. The land closest to the sea was becoming less stable. Imagine walking through one of these communities near the end of this period. You might see families building shelters on slightly higher ground, not because of sudden danger, but because the lower areas had become marshy or unpredictable. Nets would be repaired near freshwater springs instead of on exposed beaches. The walk to the shore would take slightly longer each year. Not enough to alarm people, but enough to notice. The important part of this story is scale. The changes were too slow to recognize as a single transformation, but too fast to ignore across generations. A person living at 13,000 years ago might not see much difference in their lifetime. A person living 2 or 3 centuries later might notice that a familiar gathering place no longer existed. Then another few centuries, and new river mouths appeared where none had been before. The horizon shifted quietly, patiently, persistently. This slow movement gave communities time to adapt their cultural practices. Seasonal rounds, patterns of movement tied to resource timing were redrawn. New gathering spots replaced old ones. Canoe routes shifted. Fishing grounds relocated. Social networks that connected groups along the coast stretched inland. Knowledge of tides, currents, winds, and marine behavior expanded into understanding how these elements changed across space and time. Another piece of evidence comes from inland site diversity. After 13,000 years ago, inland camps begin to show richer material assemblages. More tools, more food remains, more hearths. This suggests that coastal people were investing more time inland. They were not abandoning the coast, only adjusting their balance between marine and inland resources. The movement was not a flight, it was a recalibration. Picture a group returning to a coastal camp after a year away. The path feels familiar, but the land has changed subtly. The streams cut new channels. The sandbar lies underwater. A favourite fishing rock now sits half submerged. They adapt without drama. They shift their activities a little inland, a little upriver, a little higher on the slope. The world moves. They move with it. If we step back, we can see how human perception operates in environments that change slowly. Humans excel at noticing immediate threats, sudden storms, wild animals, rapid weather changes. But the slow shifting of coastlines requires a different kind of awareness. It demands memory, collective memory across generations. It demands stories about where the shoreline used to be. It demands careful tracking of where certain shellfish beds migrate, or where certain plants no longer grow. Archaeologists can infer this perceptual adaptation through patterns of continuity. Even as sites shifted inland, the types of tools, foods, and seasonal activities remained consistent for long periods. This means that people did not interpret the rising sea as a crisis. They interpreted it as part of a world where environments are always in motion. Their knowledge systems already accounted for change. The lesson from this period is not one of fear, but of resilience. People adapted to the rising waters not by resisting them, but by folding the change into their rhythms. They moved when necessary. They reorganized their camps. They remapped their world. They followed the horizon wherever it went. How do you adapt when the horizon moves closer every season? You pay attention. You trust your memory. You trust the land. And you move with the world instead of waiting for it to stop moving. A lake so large it could swallow modern countries sits trapped behind a wall of ice. Its surface is calm. Its waters are cold and heavy with the memory of glaciers. The ice dam that holds it is older than any living thing around it, 2 miles thick in places, pressed into shape by tens of thousands of winters. For centuries the dam has held. For centuries the lake has grown. And then, sometime round 11,600 years ago, the balance shifts. A warm season arrives too early. Cracks widen. Water begins to trickle through ancient fractures. And when the first thin thread of meltwater reaches the far side of the ice, the structure begins to break. What happens when a lake the size of a sea breaks free all at once? To answer that, we have to understand how glacial lakes form. At the end of the last ice age, as the great ice sheets of North America and Northern Europe retreated, enormous depressions gouged into the landscape began to fill with meltwater. These were not lakes in the modern sense. Some stretched for hundreds of miles. Some contained more water than all the Great Lakes combined. The walls holding them in place were not rock, but ice, massive, ancient, yet vulnerable. The reveal hidden within their structure is simple. Ice dams look solid, but they are not. They melt from the top in the sun. They melt from the base where warm lake water presses against them. They fracture internally as temperatures rise, and once meltwater begins flowing through the cracks, the dam weakens rapidly. Hydrologists studying these ancient systems compare them to natural versions of engineered dams. When engineers model their stability, they find something striking. Ice dams can fail not over centuries, but in days. The sediments left behind tell us that something like this did occur. Across parts of North America and Eurasia, we find massive sedimentary structures called megafans. These are deposits of gravel, sand, and silt, spread across wide areas, forming cone-shaped blankets that can extend for miles. The size and distribution of these deposits indicate that they were laid down by fast-moving, high-volume flows far too large to result from ordinary river flooding. Their scale matches exactly what would be expected from the sudden release of glacial lakes. One of the most famous examples of this process occurred in what is now the Pacific Northwest. There, enormous basaltic channels and deep scoured canyons carved into otherwise stable landscapes point to a giant outburst flood in the late Pleistocene. These landscapes contain boulders larger than cars, transported miles from their source and left stranded in flat plains. Geologists call these erratics, and they are some of the clearest evidence that only catastrophic water flow could have moved them. But this pattern is not unique to one region. Sediment cores taken from areas surrounding ancient glacial lakes in North America, Northern Europe and Central Asia all show similar signatures. Thick, chaotic layers filled with coarse material suddenly appear between finer, calmer deposits. These chaotic layers represent a moment of extraordinary water movement. They show that water-carrying sediments surge through the landscape at speeds and volumes that dwarf modern rivers. To understand how such immense flows are possible, hydrologists turn to models. These models simulate what happens when a glacial lake breaches its dam. The results are staggering. Once a critical threshold is crossed, erosion accelerates the breach. The meltwater enlarges the opening, which increases the flow, which increases the erosion. It is a self-amplifying cycle. Within hours, the dam can be carved into a wide channel. Within days, the lake can drain entirely. The flow rates predicted by these models match the sedimentary evidence on the ground. This rapid drainage leaves behind another signature: erosional landscapes. Some valleys show giant ripples, wave-like structures tens of meters across, formed beneath fast-moving water. Others contain scablands, rocky, stripped surfaces carved violently by flow. In certain regions, deep potholes bored into bedrock suggest that swirling currents drill downward with immense force. These features are not formed slowly. They require water moving with speed and power. One question often raised in the study of these floods is how big these lakes really were. Estimates vary, but even conservative models suggest that some contained volumes so large that their release would have reshaped entire river systems. The lakes of northern Europe, for example, may have spanned thousands of square miles. Similar lakes in North America covered land that, when drained, dramatically reconfigured the young landscape. It is important to remember that these events did not occur everywhere at once. They were regional. Each lake had its own timing, its own geometry, its own path of escape. Some drained northward into the Arctic basin. Others drained southward toward major river networks. In Europe, the lakes trapped between the retreating Scandinavian ice sheet and upland terrain released water into valleys that carried the surge toward ancient ocean basins. These floods, while not global events, were immense on local scales. The hydrodynamics of these flows are important. When a dam fails and a flood wave travels downstream, it interacts with the landscape in predictable ways. The first surge scours the ground, the second carries large sediment, the third deposits finer grains. Over time, these layers create a vertical sequence that geologists can read like a timeline. When such sequences are discovered across vast distances, they indicate a flood that lasted long enough for multiple phases of flow to occur. Ancient flood bars, raised ridge-like deposits, also support this picture. They formed when water slowed enough for sediment to accumulate. Their presence shows that the flood was not a single burst, but a sustained event, possibly lasting several days. During this time, water would have spread across the floodplain, filling basins, carving channels, and leaving behind the megafans that today serve as silent testimony. This raises a deeper question. How suddenly did these events unfold? While we cannot measure the exact hours or days, the consensus from models and geological evidence suggests that the most intense flow occurred within an extremely short window. Once the ice dam failed, the physical forces involved were unstoppable. The lake emptied with a speed governed not by the dam's structural resilience, but by the physics of water seeking lower ground. To picture the moment a glacial lake breaches its dam, imagine a sheet of ice shattering from pressure. Water bursts upward and outward. The ice cracks widen. Entire blocks break free, carried downstream by the force of the flow. Trees, boulders, and sediment churn in the water. The sound would have been immense, a thunderous roar that echoed across valleys. The flow would tear away soil, carve cliffs, and leave behind stripped bedrock. We can also imagine the aftermath. After the lake drained, the remaining basin would have been a vast stretch of exposed mud. Channels cut by the flow would still contain pools of water. The former lake bed might take centuries to refill with vegetation. The landscape would be permanently altered. Rivers that once drained gently through valleys would now run through deep, carved channels. The path of water through the region would be changed. Scientists continue to refine these interpretations. Some argue for multiple smaller discharges rather than one catastrophic event. Others support the model of sudden massive drainage. The evidence is often complex, requiring careful analysis of sediments, landforms, and dating techniques. What we do know with confidence is that the late Pleistocene produced some of the largest floods the Earth has ever seen, and they were driven by the instability of melting ice. Hydrodynamic modelling, sediment analysis, and geomorphic interpretation all converge on the same conclusion. Glacial lakes held tremendous potential energy. When released, that energy reshaped landscapes within days. The Earth's surface is full of scars from these events, reminders of a time when the last ice age unravelled with both quiet shifts and violent transformations. What happens when a lake the size of a sea breaks free all at once, the land remembers. A world you will never walk, a world where the tides never retreat, a world whose villages, hearths and toolmakers now lie in a silence so complete that even time feels muffled. Somewhere beneath 400 feet of water, there is a shoreline that once rang with voices. Children played there. Hunters mended nets. Fires burned on evenings long before written memory. And then the sea rose, quietly at first, then relentlessly. Today those places rest in the dark, and yet, strangely, we can still find them. The reveal begins with a simple truth that archaeology has always struggled with. Most of human life during the late Pleistocene and early Holocene unfolded along coasts. Coastlines are where food was rich, rivers opened into calmer waters, and migration paths moved easily along corridors of land and sea. But coastlines are also temporary. When the last ice age ended, every shoreline our ancestors knew shifted inward. Some moved by a mile, some by tens of miles. In certain places they shifted by entire mountain lengths. Each time the sea rose, it carried with it the memory of a world that was never meant to be preserved. For a long time, researchers assumed those places were lost forever. But the ocean has its own way of keeping secrets. Sediments can bury tools before waves scatter them. Cold water can preserve wooden structures. Mud flats can entomb campsites so tightly that footprints remain intact for millennia. And in the last few decades, as technology has changed, we have learned how to listen through salt water. The first step in underwater archaeology is not diving, it is mapping. When you're looking for a world drowned 12,000 to 5,000 years ago, you begin with bathymetry. High-resolution sonar surveys sweep the seafloor in wide arcs, painting the submerged landscape with sound. Instead of the blank blue of an ordinary map, these surveys reveal drowned valleys, riverbeds, terraces, and ancient lake shores. Some lie only a few meters below modern waves. Others lie hundreds of feet deeper, but the signature of the ancient land is unmistakable. It is carved and shaped by wind and fresh water long before the sea claimed it. Once submerged, topography is mapped. Archaeologists compare it with paleo-shoreline models. These models reconstruct where sea levels once stood, year by year, century by century. They show where rivers once met the ocean, where estuaries opened, where coastal plains stretched wide and flat. Those plains, now hidden, were often the centres of human activity. Still, a landscape is only a skeleton. To find signs of life, we look for texture. Scattered stone artifacts sit on continental shelves in places no tool has any right to be unless people lived there. Some stone tools recovered from sites off the coast of Australia date to periods when those shelves were dry, open land. Similar discoveries appear off the coasts of Japan, the British Isles, India, and parts of the Americas. They're usually small pieces, a flake blade, a core fragment, the unmistakable geometry of human workmanship. But small though they are, they tell a clear story. People were there. Entire communities may have been there. One technique that has transformed this work is sub-bottom profiling. Instead of sending sound over the seafloor, these instruments send it through. The returning echoes reveal buried layers beneath the sediment. In some places, researchers see straight lines where none should exist, right angles that suggest wooden posts or stone alignments. These are not the grand lost cities of popular imagination. They are the remains of everyday life. Fish traps, timber footings, hearth pits, places where families sat and cooked by fire long before water swallowed the shore. In rare cases, structures survive. Off the coast of northern Europe, archaeologists have discovered stone formations and preserved peat beds that can be traced to Mesolithic camps. The peat contains pollen, seeds, and preserved wood, all clues about the environment people lived in as the sea crept closer. Off the coast of Israel, a submerged Neolithic village rests beneath clear water, its houses partly intact, its well still filled with tools. In some places, human footprints remain pressed into ancient mud now buried under sand layers on the ocean floor. These quiet traces challenge our assumptions about loss. They show that the sea does not erase everything, it simply hides it. To gather finer details, researchers use remotely operated vehicles, or ROVs. They descend into the dark with lights and cameras, drifting over submerged worlds with a calmness that feels strangely reverent. Their robotic arms can collect sediment cores from places too deep for divers. Those cores reveal stories hidden in layers. Volcanic ash from eruptions, pollen from vanished forests, charcoal from long-extinct fires. In some cores, chemical signatures match animal oils used in ancient cooking. In others, a thin dark band marks a moment when rising water turned a thriving campsite into a marsh, and then into a lagoon. Every recovered artifact forces us to reconsider the scale of what lies underwater. When sea levels rose by nearly 400 feet, they did not simply drown camps, they swallowed entire landscapes. In Southeast Asia, vast lowlands that once connected islands are now the floor of deep seas. In northern Europe, a region called Doggerland once linked Britain to mainland Europe. It was not a tiny bridge. It was a land mass rich in rivers, lakes, forests, and coastlines. Archaeological evidence suggests it supported large communities of hunter-gatherers. Today it rests beneath the North Sea. Fishing trawlers sometimes pull up tools, bones, and antler points from its buried world. Yet we have found only a fraction of what was lost. Underwater archaeology is still young. Most of the world's continental shelves remain unmapped. Many lie under murky water where visibility is low. Others lie so deep that only specialized equipment can reach them. And even when sonar reveals a potential site, excavation is slow and expensive. It may take days of calm weather to retrieve a single artifact. The sea gives up its stories reluctantly. Still, each new discovery adds to a growing picture of early coastal life. We see traces of fishing technology far older than expected, woven traps preserved in anaerobic mud, stake alignments that once guided fish into channels, charred shells from fires used to process seafood. We see evidence of seasonal camps that moved with tides and migration patterns. We find hints that some communities specialised in marine resources long before agriculture or settled villages spread inland. A story so old that no language we speak today existed when it was first told. A story whispered beside fires on coast that no longer exist, carried across generations that never saw the waters that inspired it, yet somehow felt the weight of what their ancestors endured. A story that drifts across continents, changing shape but never losing its spine. How does an event become a memory that survives thousands of years? The reveal begins in the mind, not in the world. Human memory is not an archive. It is a living process. When something extraordinary happens, the brain encodes it differently. Stronger pathways, heightened emotion, sharper sensory detail. Neuroscientists studying trauma note that events involving danger, displacement, or sudden change crystallize more deeply than ordinary days. When those events affect an entire community, they become collective memories. They are recited, repeated, rehearsed. And the more they are told, the more they settle into the architecture of culture. Somewhere between 10,000 and 5,000 years ago, the world was in motion. Seas were rising, coasts were shifting inland, rivers found new paths, lakes expanded or vanished. These changes were slow enough to allow survival, but fast enough to be felt. A child could grow up remembering the old shoreline. A grandparent could recall a time when a now distant ridge was still part of the coast. Human groups living near water saw their world reconfigure itself within the span of a lifetime. The memory of such change did not vanish. It became woven into stories. Oral transmission is the most ancient technology humans possess. Long before writing, long before carvings or symbols, communities taught their children through narrative. Stories were not entertainment. They were instruction manuals. They were maps of danger, guides for survival, repositories of ecological knowledge. When a community faced an upheaval, they translated that upheaval into narratable form. This transformation is neither accidental nor arbitrary. Cognitive scientists studying oral cultures find that stories containing dramatic environmental events persist longer than those about daily life. The brain favours narrative structures that help predict risk. Throughout the late Pleistocene and early Holocene, many communities experienced episodes of displacement. Some moved inland as water encroached. Others adapted to new marshlands, new estuaries, new currents. These experiences were carried forward as lessons. But told long enough, lessons become narratives. Narratives become myths. Myths become shared cultural memory. One of the clearest features of oral tradition is convergence. When different societies experience similar pressures, their stories often echo one another, even across vast distances. This does not require contact or borrowing. It is a function of how memory organises itself around meaning. When the same kinds of events recur in different environments, the human response, emotionally and narratively, often follows a similar pattern. The details vary, the structure remains. Anthropologists studying oral cultures describe something called mnemonic anchoring. This is the process by which a striking physical event becomes the anchor for a memory that will be passed down. A sudden rise in water, a land bridge disappearing, a river altering course, a storm that permanently reshapes a coastline. These become anchors because they challenge a community's understanding of permanence. They mark a before and an after, and humans across all societies use stories to make sense of threshold moments. As sea levels rose, many communities would have witnessed repeated transformations of their environment. A river delta slowly drawing back, a settlement becoming marshland, a familiar bay deepening into an inlet. Such experiences may seem modest compared to catastrophic floods, but in oral memory, scale matters less than meaning. What matters is the recognition that the world itself is not fixed. When children grow up hearing their elders speak of a place that no longer exists, the loss becomes part of their identity. They learn that land can vanish. They learn that people must move. These lessons crystallize into stories of transformation. Another element in the formation of long-enduring memory is emotional salience. A community forced to relocate because a shoreline has changed will experience grief, uncertainty, and adaptation. Such emotional experiences make memories more durable. When retold, these memories carry not only facts but feelings. Neuroscientists note that emotional charge acts like a preservative. It keeps a memory alive. Over centuries, as languages shift and populations migrate, those emotions outlast the details. A community that once lived on a drowned coastal plain may pass down a story of moving to higher ground. The specific geography may fade. The emotional shape remains. It becomes a tale of water rising, of the world changing, of ancestors who survived by listening to the landscape. Within this process, a fascinating pattern appears: compression. Oral traditions often compress long periods into singular events. Slow sea level rise becomes the flood. Generational movement becomes the journey. Incremental change becomes a single moment that defines the collective experience. This compression is not distortion. It is a cognitive strategy. It allows communities to pass down essential truths without requiring exact chronology. What matters is the meaning, not the measurement. Memory leaps across generations in these compressed forms. It carries forward the essential instruction. The world can change suddenly. Be watchful. Be adaptable. Respect the rhythms of nature. These instructions are not bound to any one place. They arise wherever humans lived at the edge of shifting water. The role of ritual cannot be ignored. Many early societies use stories in ceremonial contexts. Ritual repetition strengthens memory. Over thousands of years, the story becomes embedded in cultural identity. It becomes less about the original event and more about who a community believes itself to be. In this way, an environmental memory becomes a mythological one. Yet beneath all the layers of metaphor, symbolism, and retelling, researchers find a persistent echo of lived experience. Linguistic studies reveal that certain narrative motifs, rushing waters, rising tides, journeys to higher ground, are unusually stable over long periods. This stability suggests that stories of environmental change were retold so frequently that they became part of the deep memory of entire cultures. This raises a quiet thought. If landscapes shape memory, and memory shapes culture, then the great environmental shifts at the end of the Ice Age did more than rearrange coastlines. They rearranged minds. They influenced how early societies understood the relationship between humans and the world. They taught that survival depends not on mastery but on attentiveness, and in that attentiveness memory was born. How does an event become a memory that survives thousands of years? It does so through people who refuse to forget, through stories told beside fires, through lessons preserved in narrative so that children, and the children after them, will understand what happened long before their birth. In this way, the past becomes part of the present. and ancient experiences continue to shape how we think, live, and imagine our world. What makes these deep memories even more remarkable is how they survive through disruption. Oral traditions are not fragile. They evolve the way living systems do. When communities split, each branch carries the core of the story with it. When languages shift, the imagery adapts. When people move into new landscapes, the old memory reshapes itself to fit the new terrain, but the underlying pattern remains. Anthropologists call this drift, but drift does not erase meaning. It preserves it in altered form, the same way a river changes course while still flowing toward the same sea. Another layer enters when we consider how early societies taught their young. In cultures with no writing, memory was engineered. Storytellers were trained from childhood to retain long sequences of imagery and meaning. They learned rhythm as a mnemonic device, repetition as structure, pauses as emotional emphasis. Modern experiments with oral memory training show that people can reliably transmit complex stories over many generations, with surprisingly little distortion when the narrative carries survival relevance. This is not magic. It is technique. It is discipline. It is the ancient science of remembering. Many early communities also used landscape itself as a memory aid. Certain stones, hills, or river bends became narrative anchors, not because they were extraordinary, but because they could be woven into the story as physical cues. A storyteller leading children along a path could retell the narrative while pointing to these anchors. Over time, the geography became part of the tale's fabric. Even when the landscape changed or was abandoned, the structure of the story remained intact. Cognitive scientists refer to this as spatial scaffolding. It is one of the reasons some oral traditions can transmit information reliably over enormous time spans. There is also the question of identity. When a memory becomes central to who a community believes itself to be, it acquires resilience. It is retold not only to teach, but to affirm. The story becomes a mirror. It says, "We are the people who survived." Identity binds memory to emotion. Emotion binds memory to ritual. And ritual binds memory to time. This triad is one of the strongest mechanisms known for long-term cultural retention. Some early groups appear to have encoded environmental knowledge into story cycles that were performed seasonally. Each time the cycle was performed, the memory was refreshed. These performances often involved song, gesture, or patterned speech, all of which strengthened neural encoding. The story became embodied. It was not simply spoken, it was enacted. When memory involves the whole body, its durability increases. Another aspect worth noting is the role of generational overlap. In small communities, 3 or even 4 generations often lived side by side. A child could hear a story from a parent, then hear the same story again from a grandparent who remembered a slightly earlier version of the world. These overlapping retellings created a stabilizing effect. They reduced drift. They reinforced the central structure. They enabled a memory to pass not merely from one person to another, but through a web of connections strong enough to keep it alive. And beneath all of this lies a quiet truth about the human mind. We are pattern-seeking creatures. When environments shift, when boundaries move, when the familiar becomes uncertain, the mind searches for structure. Stories provide that structure. They turn uncertainty into meaning. They transform bewilderment into comprehension. And once that transformation occurs, memory becomes easier to transmit. The mind remembers not because the event was extraordinary, but because the story made sense of it. In the end, the persistence of ancient flood memories is not evidence of perfect recall. It is evidence of something far more human, a deep need to understand the forces that shape our world, and our equally deep need to pass that understanding forward. Long after the coast changed, long after the land disappeared, long after the details were softened by time, what remained was the lesson that the world itself can shift, and that knowledge, once learned, is never easily forgotten. A morning when the world finally stops changing. For thousands upon thousands of years, coastlines had crept inward, glaciers had cracked and retreated, rivers had shifted like restless serpents, and every horizon felt uncertain. But somewhere just after 10,000 years ago, the planet exhaled. The great melt slowed. The seas reached their new boundaries. The continents settled into the shapes we would one day draw on maps. And in that long global pause, something entirely new began. The reveal is quiet, almost anticlimactic. After all the roaring meltwater, the collapsing ice walls, the flood in valleys, and the wandering shorelines, the most transformative moment is simply this: stability. Climate records taken from Greenland, Antarctica, and the sediments of old lakes show that by this time the Holocene had begun, a period of warmth and relative calm unlike anything in the previous tens of millennia. Temperatures stabilized. Seasonal patterns became predictable. Rainfall established regular rhythms. The immense glacial scars on the continent softened into fertile plains. Rivers carved gentle paths rather than violent channels. For the first time in a very long time, humans lived in a world that no longer lurched beneath their feet. This stability changed everything. When ice sheets were retreating and sea levels racing upward, landscapes were temporary, and people moved often. But after the waters found their final shores, the earth offered something it had not offered in 100,000 years: a reliable home. Floodplains along young rivers became rich with renewed sediment. Lakes that had been meltwater basins transformed into stable freshwater ecosystems filled with fish, birds, and new plant life. Grasslands expanded across regions that had once been tundra. Forests took root where ice had stood for ages. The environment opened itself like a book, offering resources in predictable chapters. This was the world that early Holocene cultures inherited. Not yet agricultural, not yet settled, but newly abundant in ways that encouraged longer stays. Archaeological sites from this era show growing diversity in tools made for fishing, gathering, and processing plants. Technology shifted not because people suddenly became different, but because the land did. When seasonal patterns become stable, strategies become stable too. Communities stayed longer at certain lake shores. They returned to the same rivers year after year, knowing the fish would return as well. They stored more, planned more, built more. Stability became a habit. The rivers themselves played a central role. Freed from glacial constraint, they meandered, depositing nutrient-rich soils along their banks. These floodplains became some of the richest ecological zones on the planet. Animals concentrated there, and so did people. Humans followed the logic of water. They always had. But for the first time in a very long time, water followed a predictable logic in return. In this more forgiving world, plant communities evolved rapidly. Grasses expanded across wide plains. Fruit-bearing shrubs and trees colonized the warming regions. Species that struggled near ice margins flourished under a steadier sun. As plant communities diversified, so did the diets of the people who lived among them. Archaeobotanical evidence from sites across Eurasia, Africa, and the Americas shows increasing use of a wide range of seeds, roots, and wild grains beginning in this window of time. Not the domesticated crops of later eras, but the ecology that made domestication possible. Stability does not guarantee change, but it allows it. Over generations, humans living in landscapes no longer threatened by abrupt environmental shifts began to build more permanent structures. Some groups erected long-lived shelters near riverbanks, Others dug storage pits to preserve food through winter seasons that were now predictable enough to prepare for. These were not yet villages in the later sense. They were seasonal homes that stretched longer into the year, places where memory began to accumulate in the ground. The coastline stabilizations were equally influential. After millennia of retreat, the sea finally rested. New shorelines formed where once the land had been distant. Bays, inlets, and estuaries emerged, creating rich coastal ecologies filled with shellfish, seaweed, birds, and marine mammals. Communities adapted to these changing resources, developing specialized tools and seasonal calendars tied to tides and currents. For generations afterward, these newly formed coasts became the arteries of travel and exchange. But perhaps the most profound transformation occurred in the mind. When a planet stops shifting so violently, a sense of continuity grows. Children grow up in landscapes their grandparents recognized. Stories can be tied to places that still exist. Knowledge can accumulate across more than a handful of generations. This continuity paved the way for new forms of planning, new forms of cooperation, and eventually new forms of society. When humans are no longer forced to move constantly, they begin to imagine futures. This is why the early Holocene feels like the quiet prologue to everything that comes later. Stable climate leads to stable food sources. Stable food sources lead to larger groups living together for longer periods. Larger groups create shared traditions, shared responsibilities, and eventually shared structures. None of this happens quickly. Most of it unfolds over thousands of years. But the foundation is laid the moment the Earth stops convulsing. As landscapes grew more reliable, experimentation flourished. People tried new strategies for harvesting wild grains. They observed seasonal animal migrations with greater attention. Some communities built the earliest large ritual structures known to archaeology, suggesting that spiritual or symbolic life expanded alongside ecological stability. These structures were not farms nor cities, but they were signs that humans had begun transforming their landscapes intentionally rather than reactively. Through these slow transformations, the world we recognize began to take shape. Rivers that still define continents today found their modern paths. Forests that anchor ecosystems planted their roots. Plains that would later support vast cultures grew dark and fertile. And human groups, no longer simply surviving change, began shaping change. When we imagine the birth of our world, we often picture dramatic inventions, tools, or discoveries. But the real beginning starts earlier, in the moment when the planet calmed long enough for humans to stay, to watch, to learn, and to build. Everything that follows, settlements, agriculture, writing, states, grows from the quiet, steady pulse of the Holocene. What new world emerged after the oceans found their shore again? A world where time finally allowed us to imagine more than the next horizon. Even after the Ice Age ended, its memory still shaped every step we took into the future. The transformation of the land did not happen only in open spaces. It also unfolded in the quiet corners of the world that were once buried beneath ice. As the glaciers withdrew, they revealed terrains that had not felt sunlight in tens of thousands of years. These were places where no tree had ever grown, where no wind had shaped the soil, where the very ground seemed young. Over centuries, cold-tolerant plants pioneered these fresh surfaces, their roots slowly breaking down mineral-rich sediments. Mosses collected in shallow depressions, shrubs followed. In some regions, entire forests rose from landscapes that had been nothing but ice, for longer than human memory can truly grasp. This rewilding of the planet created a patchwork of new ecological niches. Lakes formed in kettle depressions left by melting ice blocks. Wetlands spread across former outwash plains. In mountainous regions, animals expanded into valleys that had long been inaccessible. And in this ecological mosaic, humans found new opportunities not through invention, but through observation. They learned which plants flourished after the thaw. They followed the migrating herds that now discovered fresh grazing lands. They adapted to waters that were no longer melt-fed torrents, but predictable rivers with steady seasonal cycles. The stability of the Holocene also shaped the rhythm of movement. Groups could now time their seasonal rounds more accurately, navigating landscapes that behaved with a consistency unknown during glacial times. Predictability fostered new forms of cooperation. When food could be gathered from the same place season after season, knowledge could accumulate along with it. A generation could pass its understanding of a meadow, a lake, or a riverbank directly to the next without that place vanishing beneath ice or water. These intergenerational geographies created a sense of belonging that was deeper than simple familiarity. They were the roots from which later traditions would grow. Even the skies participated in this new order. With the climate more stable, atmospheric patterns regularized, giving rise to seasonal signals humans could trust. The return of certain birds, the blooming of specific plants, the timing of fish runs. These natural markers offered something powerful, an external calendar, not yet written, not yet formalized, but observed and remembered. It was a framework that allowed communities to plan in ways impossible during the unpredictability of the late Ice Age. And slowly, as landscapes settled and minds adjusted to the world's calmer pulse, something subtle shifted inside human imagination. When people live in a landscape that endures, they begin to think beyond the immediate. They notice cycles rather than crises. They recognize the slow return of seasons. They see patterns in migrations, in plant growth, in weather. Such observations do not create civilization on their own, but they form the mental scaffolding upon which more complex ideas can be built. This quiet accumulation of stability, knowledge, and continuity became the soil from which every later human world would rise.